I'm sorry about your week. Next week will be better. All right, happy Tuesday. How's everyone doing? Mediocre. Next week is not mediocre, maybe better than, worse than mediocre. Better than mediocre, all right. Maybe we have a distribution of how well you're doing. We could make a histogram, make it timely. So next week is break. I wanted to tell you what we're doing this week. So today we're going to introduce linear regression in the first part of class. But I think we're going to take a bit of time today in class. I want to go through practice exam 3. We're going to take most of class today just to do some practice. I'm noticing, I think this will be good as a way to slow down a little bit, just to feel a little more comfortable about the material. So that's what we're going to do in the second half. On Thursday, we have exam 3. After exam 3, what we're going to do, we're not going to introduce any new material right before break. What we're going to do instead is have sort of a workshop with your groups. So discussing project proposals and ideas for what you might work on. So I'll be here. We'll talk together. You can sit down with a computer and ChatGPT and just have a conversation with you and your group mates, and then we can just discuss as a sort of workshop after the exam. Does that sound nice? We'll slow things down a little bit. I think we're leading up to break and there's already a lot going on. So I think it's worth slowing down just a second. Okay. Also, it looks like the homework portal on Gradescope wasn't visible to you until this afternoon. Someone emailed me that it wasn't visible, so it should be visible now. If you've completed your homework and you've been waiting to turn it in, then send me an email with your homework and I'll turn it in for you. That was a mistake on my end, so you shouldn't be bothered with trying to resubmit it. So send me an email if it's already done. If it's not already done and you need a few extra days, feel free to turn it in on Thursday morning or any time before then. That sound okay? All right. Homework 6 is really good preparation for the exam. So spend the time you need to truly master that stuff. All right. Should we get started? That's not the enthusiasm I'm looking for. We have linear regression, which is really the workhorse of everything we do in economics. Every time we go to data, or essentially, if it's not like a description, like descriptive statistics, like what we did at the beginning of the semester, essentially, we're always using regression. Hypothesis testing is a way of building our way up to the core ideas in regression and testing models. But the fundamental model, or the workhorse model that we use most of the time is linear regression. So we started introducing some of these things last time, but we're going to get into essentially what regression is and part of how we use it. It allows us to build relationships or test relationships, build and test relationships between multiple variables, which is one of some of the big things we do in all, not just economics, but statistics generally. It also allows us to test hypotheses. And we're going to be able to test hypotheses in more general ways than what we've been doing with hypothesis testing using the approaches we've just been working through. And part of the idea is we often have relationships between two different variables. So remember back in part one when we were talking about exploring relationships, one way we can understand relationships is by plotting them on an X and Y graph like this. So if we have two variables, we often see relationships. We can talk about these as linear relationships. This is a positive linear relationship, which should feel pretty familiar at this point, and a negative linear relationship. We can, in some cases, have, actually in many cases, have non-linear relationships like these two. So we have, a non-linear relationship that has sort of an inverted U, and then this second one, which is it's upward sloping, but it's not upward sloping at the same rate in every X. So we've lots of different types of relationships. What linear regression allows us to do is primarily look at linear relationships, as the name suggests. But that's only at the beginning. Like when we start introducing linear regression, the babyest of all models looks like this. But as you start developing linear regression, you can actually do more complicated things. So the models we're building at the beginning are very flexible. Like we're able to do a lot of different types of things with the core model of linear regression. So yeah, the basic examples we'll be working with are linear, but we can extend them. We're just not going to do it, at least at the beginning. And then we can talk about different strengths of relationships, right? Like the two examples here are very strong, right? Like the distribution of points is pretty tight around some underlying relationship, right? So very strongly negatively related. I've put error bounds on the model itself with this line that runs through the points, and then most of the points are within some range of that underlying model. And we're going to quantify these things as we start building this model. And the same is true with the positive strong relationship. But we can have what we call weak relationships, which are when the data is more spread out around the core model. So there's sort of more variability around the line. So this underlying relationship, but the data points aren't tightly clustered around the line itself. Okay. And so we want what regression is trying to get at is like, is there a slope? Is there a line that tells us some relationship between variables, and how strong is it? So we can also look at examples where we have, like essentially no relationship. And this, one way of thinking about what we're about to start working with is that this is a null hypothesis on the slope. It's like we're going to go in and test whether there actually is a slope to the relationship between X and Y. So our hypothesis testing, we're going to be more specific about this as we start building this model. But one way of sort of conceptualizing what we're about to do with what we've just been doing is that we want to understand and test whether there's a relationship between X and Y variables. And we can have a weak relationship, like, a bunch of data points sort of scattered around. But we could also have, not much variability in the Y variable, but still have no relationship, which is what's happening in the second example. Where in the first one, we have a lot of variability on the Y-axis. So we have all these types of relationships. And what we're going to start doing is building models that allow us to test whether there is a relationship between X and Y. And what does that relationship look like? So in some sense, when you see these pictures, I want you to be thinking about a null hypothesis. And then we'll be checking whether there is a slope. And that approach builds on our hypothesis testing that we've just been developing. So some examples here, some economics type questions. So example one would be like the X variable. So on the horizontal axis, we would have advertising, and then, is that related to sales, our Y variable? You could have sort of a macroeconomics type question, which people are fighting over all the time, which is the growth of the money supply, our X variable, related to inflation on the vertical axis? That's another relationship you could try to understand. Is income related to willingness to pay for a car? Well, if you know anything about like our microeconomics models, you would probably say it is. But we could plot willingness to pay for a car against income, and you could check whether there's a relationship. So these kinds of things are what allow us to answer or sort of arbitrate whether the models we develop in economics are sort of empirically valid. And we would want a way of checking whether, if we see a positive relationship, is that truly positive, or is it an artifact of random data? So we need a way of checking these ideas. So the goal of what regression, linear regression, allows us to do is we want a relationship between X and Y, and we want to sort of understand some idea of what the relationship might be. And then we also want to test it. Is it truly there, or is it just an artifact of the data? Is it random? So the place to start with building models in economics from data is these linear type models. If you, like I in undergrad, was a little bit skeptical of linear models, I see you. I was in that position too. There's a good reason we start by talking about linear models, because they are much simpler to understand. If you remember back to your intro microeconomics class, we always start with linear models. And then if you take anything above that, you start discussing the more complicated nonlinear models. Linear models are just a lot simpler, so it's a good place to develop our intuition, which is why we're focusing on them at the beginning. But we can do a lot more complicated and fancy things. Okay, so let's just introduce the core regression model. And this, I'm first showing you the equation for what we're doing, but then we're going to talk about some of the intuition for what these things fundamentally are about. So don't let this slide look too scary. The first thing is we have this linear relationship between X and Y. And so we have Y as the predictor variable. So it's the variable that we're aiming to predict. So it's our vertical axis. And then we have these betas. If you don't like Greek letters, you can use the letter B instead of betas. We're going to talk about what each one of these means, each one of the betas. But we're also going to talk about this error term, epsilon. But if you don't like epsilon, if you don't like Greek letters, just rewrite these as B's and E's. For some reason, this is convention. People like using Greek letters sometimes to look fancy, but you can cut through all of that if you don't like Greek letters. There's a raging debate in the econ department right now whether we should be using Greek because it can look a little intimidating. Anyway, we have these B's, which tell us, if you remember your algebra from high school, like this is the intercept, the y-intercept. So it's mx plus b. So this is our b, the vertical intercept. And then this is the m on the x. So it's like, if we want to understand the relationship between x and y, we would want a vertical intercept, and then we'd want a slope. So that's what these b's are doing. B1 is giving us the slope, and B0 is giving us the vertical intercept. But it's the same thing as mx plus b. So these are the coefficients, but there's this epsilon on the end. Everything we do with data is going to be noisy. Remember, we're randomly drawing from a population, and there's going to be sort of error. So every type of measurement we make, when we look at data, we see that it's noisy. And so what epsilon is doing is giving us some way of expressing that noisiness. So mx plus b, every point on the line is precisely on the line. But when we go to data, that never happens. There's always going to be some variability around a relationship. And so what epsilon is doing is expressing that noise around the fundamental relationship between our y variable and our x variable. Okay, so this is the simplest regression model. But we can also do more fancy things, which is some of you may use multiple linear regression in your projects. We're going to come to multiple linear regression a little bit later. It's a little more complicated. There are some places you have to be sort of careful. But fundamentally, what we're doing is we're just introducing multiple variables. So like y is a function of multiple things. So we'll come to this a little bit later. I just wanted to show this to you on the first slide, just to let you know that we can do more complicated things than just one variable as the predictor, and one variable as the input. Okay. Any questions here? So fundamentally, what we're doing with linear regression is trying to test whether beta 1 is there or not. Is beta 1 0, or is it not 0? Beta 1 is the slope of the relationship between x and y. So is there a relationship between x and y? So that's sort of the main question. Where before, in the past, we've looked at x bar. What we're doing in linear regression is swapping out our x bar with our beta 1. We can also do the same thing with beta 0, but we generally don't care as much about it. Okay. So we have our outcome variable and then our predictor variable. Our data is essentially this pair of our predictors and our outcome variables. And we assume that y is a function of some kind, a linear function of x. With linear regression, that's one of the core assumptions. Like I talked about, we can start relaxing these assumptions as we build more complicated, more fancy models. But going into it, that's going to be our baseline assumption. And then the core idea is that we want to try to explain y using our x and see if there's a relationship between the two. What that also does for us is gives us an ability to predict y. So if I know x about you, I may be able to predict Y about you. And so that's the basic idea with building models from data. So if I know your income has gone up, then I may know something about how likely or how willing you are to pay for the car I'm trying to sell. So those kinds of relationships. Okay, so let's talk about some cars. How about? Okay, so we have a car dealership, and they're trying to understand how much someone is willing to pay for a car. We have some a range of cars, and we want to know the type of car maybe someone might be interested in. And what we're about to start talking about is an example of using income as a way of getting an estimate of maybe the type of car that the customer is wanting to buy. Can we use income to predict the customer's spending? And then we also want not just what does our model tell us, but also how accurate is our model? Because we could build a model, but maybe it's not that accurate. Maybe it tells us something, but not a lot. And so we want a model that can do both of those things for us. Give us a prediction, but also give us an estimate. So here we're trying to, our two questions are, what are we modeling? And how do we interpret the model? Before we start building up our linear regression models, we have some assumptions. And I've mentioned some of these already, but at least when we're talking about linear models, the baseline, we will complicate these things a little bit later. But the baseline assumption is that X and Y are linearly related. Some people call this the tendency, sort of the core underlying assumption of the relationship. And we will use some of that terminology as we go through. But in simple terms, we're just assuming that the tendency, the relationship between X and Y is linearly related. And then on top of that, we're assuming that the error term, sort of the variation around the tendency, is normal, follows a normal distribution. So it's sort of randomly distributed around the tendency, which gives us our error terms. Okay, so I'm going to show you some pictures about these things. I think it's much easier to understand with a picture, but these are the baseline assumptions. So we have the error around the tendency, and then the error terms follow a normal distribution. Okay, so let's look at some pictures. We have a lot of math we could run through if we wanted to, but this class is focused on building the models and understanding what they're doing, but we don't need to get into the math too deeply. You have to see it, but we want to focus on how do we use this stuff. Okay, so on the vertical axis, we have price, so price of a car. And on the horizontal axis, we have income. So how much do you make? And then how much are you willing to pay for a car? So you've probably all seen like a scatter plot with a line through it, like a line of best fit. This is fundamentally what a regression will do for us. It will find a line that fits the data the best. And this is generally how we write the equation of a line. We have B0, which is the vertical intercept of the line. So where does it hit the y-intercept? And then we have beta 1, which is the slope. So it's rise over run. So we have a run of 1 and a rise of B1. So we have the relationship between the two variables and then also the vertical intercept. That's what this thing is doing, the equation of the line. Okay, and what we're saying with this linear regression, we can define the what we call the tendency, or this sort of baseline model. It gives us the expectation of the y variable, so the expected value of how much you're willing to pay, given your income level. And this is what we call the tendency. So this is just sort of this is fancy notation. Sometimes this throws me off a little bit that we write it like this. This is fancy notation for a simple thing. We have a line, and that line we assume is generating the data. But we also have observations, right? And these observations don't perfectly live on the line itself. So the tendency doesn't perfectly predict the line doesn't perfectly predict the data. And it's like anytime we talk about random things, there's going to be lots of underlying randomness, right? I wake up every morning and I'm never perfectly able to predict what I want to have for breakfast. So there's like underlying randomness inside all of us, right? Like that's like decision making has some element of randomness. But then there are also other things like, maybe I ate a small dinner, so I want a big breakfast. I wake up really hungry. There are other factors that can influence the predictor. So in this case, when we're thinking about how much people are willing to spend on a car, there are other factors that might influence how much someone's willing to spend on a car. If they're buying a second car, they may be willing to spend less because they already have one car, and the second car is not totally necessary. So they might be willing to spend less, but maybe they'd be willing to spend more. There are other factors that we may not observe in our data set that lead to these deviations from the tendency. So there are lots of reasons underlying why data might be sort of randomly distributed around the tendency. And we can't always, in fact, we basically never know all of them. At least I've never seen an example where we know all of them, at least in social data. So what we do instead is we put it all in the error term. We say there are lots of unknown reasons why our model isn't perfect, and we call that the error. So we have the tendency, which is that core line, and then we have the data, which is the actual things that we see. And there's a reason. Well, we'll come back to why we call this the expectation of y given x. But these are sort of the two sort of core ideas that we separate out. We have the underlying model, and then we have the data around the model, which is random. Okay, so we have the data, we have the underlying model, and we're just going to walk through sort of a visual way of understanding what the error is actually doing. So we have some data point. So a customer walks in, has some level of income, and then is willing to pay some level for a car. So we have two pieces of data. Like we can see how much they make and how much they're willing to spend. And this puts us at a point on this XY plane. So it's one example of a piece of data. On the x-axis, right, we're at a point on the horizontal axis, which represents the income level. And then on the vertical axis, the prediction is the model. So we have beta 0, which is the vertical intercept. But then on top of it, we have what the model tells us from the slope. So we start off and we continue to increase. We essentially just plug in our x into this relationship, and that tells us the predicted y. So what does the model predict that this person is willing to spend? But then we also have the observed y. So the model predicts beta naught plus beta 1 times x. But we can also observe just that the person is willing to spend y. So the model is going to be wrong, at least partially wrong. This is what we call the error term. So this is that the epsilon itself is some difference between the prediction and what we actually see. So fundamentally, all of our models are going to be wrong to some degree. So this is just a way of visualizing the wrongness of the model. So we have y, and then we have the prediction of y, and then the difference between those two things is our epsilon. Okay, and then we can just run through a couple of examples. Here, the prediction actually overstates how much the person is willing to spend. So it's beta naught plus beta 1 times x, but our y value is below the prediction. So in this case, the epsilon is negative. So the model is predicting that the person is willing to spend more than they actually are willing to spend. So we get an error term that's negative. The core assumption, you'll remember we talked about the error term being normally distributed. The core assumption is that we get a normal distribution of the errors around the model. So we have this baseline model in green. We have the data being distributed because there's randomness in all of our data. And then around the model, we get this normal distribution. And it's not just at one particular point, it's actually everywhere. The assumption for the normal for linear regression to work is that the underlying error term is normally distributed around the model. So the data is normally distributed around the model. This is another way of saying that the error term itself is normally distributed. These are two identical assumptions. The error term is normally distributed, which we say here, which is a way of saying that the data is normally distributed at every point around the tendency. This is a really powerful picture. This is how we visualize the underlying assumptions of linear regression. Okay, any questions here? Nice. Okay. So we have an error term with a normal distribution centered on 0 with some standard deviation or variance around the model. Okay. And this is the full description of a linear model. We have beta 0, which gives us our intercept. We have beta 1, which gives us the slope of the relationship between the two things. And then we have the variability of the error term. When I first saw these things, I thought the error term was sort of just like a nuance or like something to put up with. But fundamentally, the way we measure the model is using the error term. It's a really powerful part of linear regression. Okay. So the basic idea is this, right? We have some relationship between the data points. We're fitting a best line, and then we have error terms distributed around that central line. And the assumption is we have some relationship underlying, which is generating our data, but we don't get to see all of the data, right? We're only doing the sampling. So these pictures are sort of showing the sort of analogy between what we've just done and what we're doing. The reason we did all of this hypothesis testing is because we can apply it to these models. We sample from the population itself, which we assume has some underlying model, right? Remember, we were talking about an underlying model where we can sample from the population. There's some distribution. We don't know what it is, but the central limit theorem tells us that if we take repeated samples, we will eventually get a normal distribution with a standard deviation that we can, observe from our sample. We're doing the same thing here. We're taking a sample from the population, gives us a relationship in our sample data. But there's, and we're assuming there's an underlying relationship. And what we're doing with linear regression is trying to get at the underlying model. But we don't see it. What we see is the sample. So everything we're going to do with linear regression, it basically follows the same approach as what we've done with hypothesis testing. Central limit theorem tells us we can do all these things, even though we don't see the distribution or the underlying model. Just we're taking a mean and replacing it with a model. That's the idea. It's really powerful stuff. Okay. So everything we do with regression, it allows us to do hypothesis testing on the model and not just on the mean. And our computations are really involved, like they involve hypothesis testing on the sample, building models and testing the models on the sample. Yeah, Tony.
So if we do a sample linear regression, will it be like a little bit off with the population linear regression, or do we just use
Yes. No, exactly. So what we're doing is we're actually running the linear regression on the sample. We assume that this is what the truth looks like, but just like in hypothesis testing, we're never going to be able to see the truth. We know that, like a coin flip, we know what the truth is. It's 50-50. Every time we flip the coin, it either comes up heads or tails. And that's the thing we observe. And so we're making claims about the heads or tails of the coin based on the observations of the coin flips. So we can't see everything about the fundamental relationship between income and willingness to pay for a car, but we can see some of the sample, and then we're going to use that same idea of like we can observe some of the stuff to then say something about the population that we never observe. Yeah, great question. What else? Okay. Does the analogy work for you? Nice. Linear regression is it's like a fancier way of doing hypothesis testing. We can do the simple way with linear regression too, but it allows us to test more complicated population models. Okay, so this part, we do all the computations, which give us the parameters beta 1, beta 0, and sigma. All of that's going to be done in this class in Python. We're going to do a lot of these things, and it's going to look very similar to what we've done with hypothesis testing and confidence intervals. We can build confidence intervals around the betas, and then we're going to test them against 0. All right. So just to write out some notation here, we have a population model. So we say, this is what we think the model looks like. So it's like, when I flip a coin, I know it's going to be random around some probability of coming up heads, right? There's an underlying model. Coin flipping is a very simple model, but we can do more complicated models like this, where we have a line relationship between variables. We have the error term, which is saying that our underlying data is noisy, like there are other factors involved. And then what we're doing is building a regression model. So we have this thing, these beta hats tell us that these are estimates. So it's sort of our notation for estimates. So we have this population parameter or population parameters. But then we're trying to get estimates of those population parameters, which we call population statistics or population characteristics. So these are our beta hats and S, which is the same notation as we have been using in hypothesis testing. Okay. So we're just going to walk through a little bit of how we actually build these models, estimating the regression line. So, we have this line, and we have some actual. We're going to walk through how we talk about the models themselves. We're not going to talk about how we test them. We'll get to that after break. But here we have the actual model, the actual data point, and then we have the prediction from the model. So we see someone walk in with an income of Xi. We can plug that into our model to get Y hat, which is the predicted value of Y. And this is what we call the residual. So this is whatever our model predicts, there's going to be error. Just like we talked about the error in the population model, here we're saying there's a prediction that we're making using the model that we've built. So fundamentally, this is different than the green line we drew before, right? This is the predicted model, not the truth. So we have the yi, we have the prediction. This difference between the two things are not epsilon, but e, is the residual. And this is all stuff we can see. So we can see, the data, and we can see whatever model we've built. So that's what we call the residual. We can look at the residuals for all of the data points we have. And this is what allows us to actually build the model. We may not know yet what the y hat is. So the idea with building these models, we're not actually going to do any of the math. We're going to let Python do all of the heavy lifting. But I want you to understand where how we get the best fit line. It comes from some kind of involved calculus. You may have seen it before, actually. Some of you might have. So we have the observed data, we have the estimated data, and then we have the residual. The residual is this difference between the prediction and the truth. So then we have a bunch of data points. We have all of these residuals for all of the data points. And what we're trying to do is pick these betas, the beta hat 1, beta hat 0, such that the residuals are as small as they can go. But specifically, we want if we just minimized the difference, minimize the residuals, a value above the estimate would be different than a value below the estimate. So if we were trying to minimize just the difference between the model and the error, we could make the model say very large numbers, and that would make our residuals very small. What we actually want is for the residuals to get very, very close to 0. We want the errors to be as small as possible, but not negative. So what we do instead, for sort of calculus reasons, if you want to take a first derivative, square terms are really nice, which is why we use squared. And what we're trying to do, instead of minimizing the difference between the prediction and the truth in sort of absolute terms, we're going to minimize the squared residuals. And this makes the calculus actually work out. So that's there's a first derivative reason why this is called the least squares method. We're trying to, so we're adding up all of the squares, which comes from the sum of the differences between the truth and the model, where the model, remember, is made up of beta 0 and beta 1. Is we're just taking the squares of all of the residuals, and we're going to find the betas that make the residuals as small as possible once we square the residuals. Okay, I've said that a couple of different ways. We don't need to get into the details of how we actually perform this operation, but there's really nice mathematics. It requires some derivatives and like a bunch of algebra that we're just not going to do in this class. If you want more information on this stuff, and if you love it, you can take econometrics. There are courses devoted entirely to this stuff. It's not what we're aiming to do in this class. We let Python do the work for us. Really nice Python packages that can just do this instantly. Okay, so that's the least squares approach. Any questions about any of this? Do y'all want to do some practice? All right. So we're going to spend some time walking through example 3. On Macs, you can hit a button and it brings up emojis, which is nice. All right, so let's. We're going to spend the last half an hour of class just walking through example 3. We will return to linear regression after the break. It's really where a lot of the tools of what we've been doing in this class come together. We're going to talk about how we think about building the models and how we interpret them. This is the last part of the class, is using these models. And we're going to do it all in Python, but we're going to do it step by step. None of it's going to feel overbearing. Okay, so you've maybe seen example 3 on the part 3 page. What we're going to